Okay. So today and next week, we're going to continue discussing Discover with some hands-on tutorials following along with some example projects. Sure. So I showed you this matrix last week. As part of developing Discover, I put together a few of these case studies. These are kind of test problems for optimization that involve like geometric aspects. So if you study optimization, when people develop these algorithms, of course, there's a lot of different algorithms out there, and you often need to fine tune the parameters of those algorithms to make sure they work. So the field has come up with a bunch of these test problems to basically test if the optimization process is working correctly. So these are problems where you know the answer, you just want to see how fast or efficiently the algorithm gets to it. Unfortunately, in the field, most of the problems that optimization deals with is expressed through like equations and things. So that's a lot of test problems you'll see. Discover will work on those kind of problems as well. Like you can just put in an equation in Grasshopper and optimize it. But because I developed this tool specifically to work with geometry problems, I've been developing also a series of kind of geometry-based test problems that are kind of similar in idea. These are problems we know the solution to. We just want to see if the algorithm can get to the answer and how quickly. And I've developed them to basically test different features of Discover that we went over last time. So we're going to look at a bunch of these problems today, mainly dealing with looking at different input types. So we're going to look at continuous type input parameters, categorical, and also permutation. And we're going to look at both single and multiple objective problems. And we're going to do that today for about an hour. Then I'll meet with you guys to discuss your projects. And next week, we're going to do the same thing, but we're just going to focus on one particular issue, which is the constraints. So we're going to leave constraints all the way until the end. And then the week after that, so 3 sessions from today, we're going to have the last lecture, which is all about documentation and visualization. So I'm going to show you how to, working between Grasshopper and Discover, create some visualizations that are specific to the optimization process. So we're going to look at creating GIFs, creating videos at different design iterations, creating overlay images where you can actually start to composite different generations of designs on top of one another to see how the evolution process is unfolding, and then also exporting the scatter plots and things like that. Any questions before we get started? So a couple notes. First, here is the repository page. Make sure that as you're working through this, like every time you get started for the next few weeks or so, check if there's been any updates here to make sure you have their latest version. Because as I'm testing this thing myself, I'm always updating code, fixing small bugs. This is a very kind of nascent version of this project, so I don't have any kind of major releases. It's just basically updated as I go. So if you look here, 28 minutes ago, there's an update, and you can see here the description of what was updated. So if anything like fixed bug in constraints, you definitely want to make sure you have the latest code because I just found these bugs last night. This is nothing we'll deal with today, but for next week, it's going to be important. And remember to get Discover on your machine. If you're not using GitHub, I just download the zip file directly from this website, unzip it, and then it lives here in the in your folder structure. Now with Discover, you get a few of these samples included. So if you go to Grasshopper, here are your components that you drag and drop into Grasshopper, and then the sample files are here. For most of them, it's just a Grasshopper file. The traveling salesman problem we'll look at today also has a Rhino file associated because we're importing some geometry from that. In addition, as I'm running these test cases on the new version, I'm saving out a couple of the test runs so you can see, and we'll take a look at these today probably, basically examples of data output or like optimization data sets. And those are too big to sync with GitHub, but I have a link here to download sample optimization data. You can open it up. It'll be a Dropbox link with some zip files. These zip files are actually versions of the folders that are created when we run optimization. So you should be able to unzip these and load it up in Discover as you would any optimization that you run yourself. We'll take a look at that in a little bit. Okay, so why don't we get right into it. I'm going to start with the pill example that we looked at last week, and we'll start with a version without interfacing with Discover, and I'll show you how to get that up again from scratch, and then we'll look at a lot of these pre-built examples. All right, so the first thing I'm going to do is just open Rhino. My Rhino window here. We're not going to do much in Rhino for these demos. It's mostly going to be Grasshopper. So I'm just going to immediately launch Grasshopper. And I'm going to start with this example pill start. This is the only example file where it doesn't actually have the Discover nodes already in there. So we can just have one example of creating those Discover nodes from scratch. So I'm going to load this in. Now here's the example. So this is just the geometry part. And I have this example that we've looked at before. It basically starts with a NURBS curve, and there's 3 parameters. And the parameters basically control the width of the offset of the middle of the curve, and then the top and the bottom, and there's a surface of revolution. So you can basically create these shapes anywhere from like a kind of hourglass shape to a sort of perfect sphere. We're going to use this very simple model to test how well the optimization can optimize a single objective, so the surface to volume ratio of this object, as well as multiple objectives, looking at surface volume, area and volume separately. So in the beginning, this is a single objective problem we'll look at. So you see here, there's the cap to form the solid. We're calculating surface area and volume, and then just dividing them. So this will be our first single objective. It's the surface area to volume ratio. And you see here, I have this Galapagos gene pool. Just get it from the basic Grasshopper components. This is a really good way to test your models before you hook them into Discover. I've tried to make the Discover interface and the specification of each optimization job as simple as possible. So you're selecting from presets, but it still takes some time to like get that going. So when I develop my models, as I'm developing before I start the optimization, this is a really quick way to test them. These gene pools are great because number one, you get a set of parameters, so you can double click and actually say how many genes are in the gene pool. That'll be the number of parameters, and they all share the same range. So this is very similar to the way that we specify input parameters in Discover, right? We have multiple parameters, but each one can be of different lengths. So here, it's we can directly convert this to a continuous parameter in Discover with a 3 length setting, right? The other cool thing about gene pools, you can right-click and randomize the values really quickly instead of like scrubbing different sliders to test your model. You can just start generating random designs immediately. So with my model, I'll typically start with these gene pools and then convert them to Discover parameter sets when I'm ready to optimize. Oh, by the way, feel free to ask questions as I go if you have any questions or
is there a way to update the number of genes you have based on the variable?
There is not at the moment. Yep. In the next version, I want to make smarter Grasshopper components that pull that automatically from the Discover server. But with these gene pools, no. You have to specify by double clicking.
Within Discover?
No, we'll see that because of the way it works, you can use these explode tree components to basically automate that. So you bring in, Discover will output trees of parameter sets, and then you can use these, and if you right click, you can do the match outputs. And that will automatically create or separate out all your parameter sets. But in the future, yeah, it'd be great if the Discover component itself, when it imported, create those outputs. It's possible, but it's not implemented yet. Okay, so let's just start, say this is our model. Let's just go step by step into how to get this working with Discover. We can start with our Discover components here. And the first thing we always want to do is create a connect component so that Discover can see our Grasshopper model and vice versa. And when you first create this component, it'll take a few seconds because right now there's no server running. It's actually checking the server. It's waiting for a timeout. This will take some time. Obviously, when you have the two connected, it won't take this long to run these things. It's just the nature of it checking that network connection and taking some time. Okay, so right now we don't have any server running. So before we do anything else, we want to start that Discover server. I'm going to use the Docker implementation here, but remember we can use the straight Python one as well if we want. The Docker one's just easier because if it's working, it should just require one run of this batch file and everything else will be automated, including any updates and things like that. Okay, so this should load up. So here's our interface. And now that the server is running, I'm going to go back here and I'm going to create the connection. And to test the connection to the server, we're going to create one of these button components. It just triggers a true false. We're going to connect it here. And when that's false, it's going to trigger a connection to the server. And you see now here, the connection has been recognized and our file has been brought in. Or the file name has been brought in here, and that's what it's going to use to name our optimization runs. Okay, so everything's connected. We have our status here. Let's just say server connected. And then we have our two connection components. So the first one is to sync up the inputs, and the second one is to take the screenshot. So let's create explode tree component. And we'll just graph the input, simplify it, and go to match outputs. Now, I use these a lot. These come built in with Grasshopper. I just use them to split out multiple lists of data into separate outputs. So if you have a list of things, here's two connection paths. You graph it, simplify it, and then match outputs, and I'll put those two connection paths on two different outputs. Okay, so I'll drag that over, and then I want to take that connection and use a read file component to read in that connection. I'm taking that first connection from Discover. Read file will read that connection. And then I'm going to plug the output of that into the get inputs component. Here. Copy and paste this panel so we can see the output. It says it received some inputs. Okay, but it's empty now. We haven't actually generated some inputs. This is just a standard success message. It's connected to the server. We haven't sent any inputs yet, though. Okay, so once we're at this stage, we can schedule some test inputs from Discover just to make sure it's working with our model correctly. So I'm going to go back here, and I have a basic input set up. It's continuous by default. All I'm going to do is change the length here to 3. So I'm going to get 3 different input parameters. That's what I want. And then the max here, 5. That's what I'm using in Rhino. Remember, this should be the same exact thing you have in your gene pool. Here I have 3 genes, 0 to 5. I specify the exact same thing here. And if you're using categorical parameters, we'll see this in a later example. You can also test them with the gene pool. You just want to round down that number that's coming out of the gene pool, because gene pools are always decimal parameters. Okay, so once we have that input set up, we can go to test. I'm just going to bring this over here, bring this down. I just want to make sure that when I hit test, my input parameters are coming in through this inputs node. If I hover over here, I'll see now instead of none, I have something there. It's a Python list, actually. Right? That's how things come out of Discover. And so the next thing I need to do is I need to just convert that Python list into a Grasshopper list. It's a bit clunky, but there's a kind of quick hack for this. If you plug in a Python list into a Python node, and then in this Python node, just delete everything and type in a equals x. And it's going to take a and set it to the value of x, but in the process, convert that Python list into a Grasshopper list. So now, if we hover over a here, we'll see that we have those 3 numbers. So this whole, like, this extra Python node, this isn't part of anything about Discover necessarily. It's just the fact that because these things are coming from Python, they're by default in the Python list. We need to convert them using this node. And now we have our 3 parameter settings. And now we can take a look. We have 3 numbers coming in as a list, and here we have 3 numbers coming in from this gene pool. And I'm grafting them here, but actually they're in a flat list. So this is exactly what we have, so we should be able to just drag and drop this to replace our gene pool. And now Discover, the inputs coming from Discover are controlling our model. So I typically will kind of replace these things, but keep the gene pool around. So I can always hot swap it. If I want to test the model, something's not working with Discover, I want to make sure it's not the model that's broken, and test it. And I can always just replace the inputs from one to the other. And now that those things are connected, I should be able to hit test and have Discover driving the Grasshopper model directly. Okay. So those are the connections on the input side, and that's what this test button is here for. Before we start the optimization, we want to make sure that everything is hooked up right and the parameterization is right to control the model. We don't want to run the optimization to figure out that our parameters weren't working correctly. Okay. So the next thing we want to do is set up the outputs. So I'm going to go back to Grasshopper and create one of these send outputs nodes. And these will just take a flat list of outputs and send them back to Discover. And what I like to do is first create a merge node. If you ever watched me teach Grasshopper, I love these merge nodes. I've never seen anybody use them to the extent that I do. But I think they make everything really clear. For example, it is possible to input multiple things into a single input. You'll see that done all the time. I think it's very confusing because there's no way to tell which thing is first, what order it's in. And sometimes that doesn't matter, but a lot of times it does. So I like to use these merge nodes to make that very explicit if I'm trying to combine data sets. And the other thing it lets me do is you can control the number dynamically. And I always try to, if I know I want a flat list coming out of this, and this is absolutely a must for this node, if you put it in a tree, it's actually going to run that node multiple times, and it won't work as expected. So you absolutely have to make sure that the thing that comes in here is just a flat list of numbers. And to ensure that, I can use these merge nodes with flatten flag in front by right-clicking, going flatten. And now I'm sure that whatever values I put in here, they're always going to come out as a flat list because they've always been flattened before they hit this node. Okay, so since we're just starting with a single objective problem, I'm going to take my objective here, the surface to volume ratio that I've calculated, plug it into merge, and plug that into outputs. Yeah, obviously here I don't need a merge, but it's going to let us expand that into multi-objective very easily in the next example. All right. And once I have that, plug in here. This is the status readout. You don't connect anything to this node. This kind of ends the process of this iteration. Okay, so the way it works is Discover is scheduling all the designs. It sends inputs and waits for Grasshopper to process those inputs and send it back a set of outputs, and then it schedules the next set of inputs. This is kind of iterative process. So you always have the inputs nodes at the very beginning of your file and the output node at the very end of it. And so this should all be working. The last thing we need to do if we want to capture screenshots from each design iteration is we want to create this screenshot component. And this connects to the second connection coming out of Discover. So we want to create another read file component connected to the second connection and then connected here. Because we haven't started the optimization yet, there haven't been any screenshots captured, there haven't been any commands sent to this connection, so this will be red when you first start. It's just saying that connection file doesn't exist yet. And then just for completeness, we'll attach a panel to the output of that. That's also a status indicator. Okay, so everything's good now. It says there's not a job running, so these nodes won't do anything until they actually start the optimization job. Just for a bit of background, if you're curious, the reason why there's two separate connections, one for inputs and one for screenshots, is because we want to make sure that everything is completely calculated and visualized in Grasshopper before we take that screenshot. So Discover will actually do two separate communication channels and first load the inputs. Once it gets the outputs, then it'll take the screenshot. And this solves any kind of visualization problems you may have, like, for example, libraries like the human library that lets you do a lot of custom visualization. Some of that stuff happens at the very end, so it won't be captured if you take a screenshot in just the normal, graph. Okay, so now we have everything connected. Let's give it a shot. So we want to make sure we're specifying our output. We have a single output, it's an objective, and we're going to minimize the surface to volume ratio. So we can just keep this as default, or we can rename it something more meaningful. Okay, and this defaults to some very low numbers. We're just going to run a 4x4 optimization for designs and 4 generations. Keep the default 5% mutation rate. I'll keep it at least at 1 and make sure save screenshot is activated. I'll start optimization. And we'll go back here. We'll see that this floating viewport has launched. This is the actual viewport that we're going to capture the screenshot from. It should automatically zoom to the extent of your model, but you're probably going to want to change this view to exactly what you want to capture in your file. I have a feature I'm going to implement very soon, which allows you to launch this preview window before you start optimization. For now, you kind of have to run the optimization, but then once this window is open, you can drag it around and change the view to what you want, and this will stay consistent for the next run. Okay, so we've run the optimization. It's actually already over, and it's preloaded the name of that last optimization run here, so we should be able to just hit load data and maximize this and see the results. So remember, in this Explorer window, we have a scatter plot, basically, that allows us to control 4 dimensions of that scatter plot. So each design that's been explored is a dot, and we can control how it's mapped to the X and Y axis of the scatter plot, and also its color and size. So here you'll have basically which features of the data coming from optimization are mapped onto which axes. If we start with a single objective, we have only one objective here. You see it says minimize surface area to volume. And then we automatically get ID and generation. So ID is the number of the design, right? The higher the number of ID, the later the design came in the optimization. And we also have separated generation. That's the generation number. And so with a single objective problem, by default, you'll get generation mapped onto the x-axis and your objective mapped onto the y. This is very intuitive for a single optimization problem. We're basically tracking what is the value of the objective on the y-axis over time, right? And because we're looking at generation, we're rolling up the designs of every generation into a column. So I use this kind of view a lot, especially for single objectives, but even for multi-objectives, basically see how each generation improved upon the last through the process. And you'll see some very intuitive things. For example, the first generation is blue dots. So there's 4 blue dots, right? 4 designs for each generation. And the first ones are random, so you get a lot of bad designs. It's high in our surface to volume ratio. But then very quickly you get this convergence, even in just 4 generations. Now, this scatter plot is totally dynamic. You can click the little mouse button and drag it. You can zoom in and out using your wheel. And you can also zoom the axes separately just by doing the same thing while on the axes. So if you go to the axes, you can hit your middle mouse button, and this will just pan that axis. By the way, this is blown out. It looks a little bit better. There's like grid lines and things in the real one. So we can scrub this up, and we can scroll our wheel here to just scale up that axis. And we can do the same thing on the x-axis as well. So we see here is basically, when we first open it up, it looks like everything converged very quickly. But if we zoom in this axis, we'll see that, in fact, almost every generation, we're getting one design that's a little bit better, right? So in the first generation, this was the best design, and then the second one got a little better, and so on and so forth. Okay, the buttons down here give you some control over how we're looking at the designs. So load data, you can hit that at any point to reload the data. We'll see that you can actually use this to update the visualization as you're running the optimization in real time. Isolate optimal will just show us the best result. Remember, with a single objective problem, there's always one best result, right? Because we have a single objective with a goal, say minimize, there's always going to be one design that's minimal. There might be multiple designs that have the same, but it always give you the first one. In this case, we actually have the best design in the last generation, which is something you like to see, right? That we're doing better and better. In this case, I might say I should run it for longer, right? Because if we get the best design in the last generation, then maybe in the next generation we do even better. So a lot of times, like how many designs per generation or how long we want to run the optimization for, that's up to us. There's no right answer, right? It's kind of like a rule of thumb. And I'll show you a few of those today about typical kind of setups. But really, you want to use your eyes and you want to use this kind of explorer to understand how the thing behaves. And what you typically want to see is you get better and better and better, and then for a few generations, maybe you don't get better anymore, and then you can stop the optimization. If you run through all the generations and it seems like it's still improving, you might want to run the optimization for a bit longer. Okay, so that's isolate optimal. So you can click that, it'll isolate just optimal designs. And then isolate selected will just isolate to the designs we have selected. Now let's look a little bit more at the interface here. As we hover over the designs, we'll get the design number. That's the design ID and the screenshot that we captured. If we click on the design, it's going to go over here into the selected designs menu. And we can select as many designs as we want and store them there. And then as long as you don't have an optimization currently running, you can also, let me get this one because it looks, oops, it's a little bit different. So as long as we don't have the optimization currently running, we can go here to our selected designs, and when I hover over the design ID, it gets kind of highlighted. If I click that, it'll actually send those inputs back to Grasshopper. And it'll actually send just the raw input data. So it's not even that you have to have the same Grasshopper file open, which you optimize. You just have to make sure that you're handling those inputs correctly, right? So even if we change this to a multi-objective problem later, as long as the inputs work the same way, we can use this previous run to instantiate different designs from our data set. Okay. So if we have design selected, you can click this button to basically just isolate only those designs. So we'll see this again in a couple of weeks where we talk about visualization, but you can start to use this to create visualizations of the scatter plot. Right now, there's not really an export to Illustrator function or anything like that, but we can capture screenshots and we can basically use this interface to select the designs, isolate them, so we can overlay those two graphics, and then also start to bring in those screenshots into our visualization. Okay. Really quickly about the axes here. These are dynamic. So as you select different things here, the data will actually transform. And this is really useful when we start to look at multiple objectives, to not just plot the data according to those objectives, but to toggle between them and see how the data moves. That kind of dynamic element really gives you a view into your design space and how these different objectives and metrics are related. For now, we don't have much to work with, so you can quickly see the kind of comparison between the generation output, which rolls up your designs into the generations, and the ID, which will give you actually in sequence of time. I think the generational view is actually more useful because remember, each generation is generated all at once, looking at the generation before. So there's not anything actually meaningful about within one generation, one design coming before another. These are all done randomly. So I think it's much more meaningful to actually look at these things generation. Okay, so now that we have the single objective version, let's just quickly change it to a multi-objective problem. For now, the best practice is just to restart, reload your browser to reset all the input and parameter settings, and also reset the browser. There's a few bugs right now with the Explorer, like if you change anything and rerun it, the Explorer might not work correctly. So just hit reload on your web browser. We're gonna set up this parameter again. And then we're gonna add an objective. Let's go back to Grasshopper here. Instead of looking at surface area to volume ratio, I'm actually gonna add another input to the merge component. I'm gonna delete this divide. I'm just gonna load the area and the volume separately into my merge component. So I'm gonna have both objectives coming back into Discover. I need to make this match here. So my first output was area, the second one was volume. And this will match the order basically that you have in Discover. This is why it's so important to use that merge node to be very specific about the order as well. So here we have surface area, here we have volume. They're both objectives. Here the goal should be to minimize the surface area, and we're going to maximize the volume. All right, so now we're going to get a collection of designs that solve that trade-off differently. We're going to keep the 4 and 4, just do a quick optimization, and then hit start. Okay, so we should see designs being generated. Here you have an output. It's going to tell you every time it starts a new generation. And you can see when the job is finished. You can go load data. And so here is, again, 20 designs, right? But now we have 2 objectives. And so when you have 2 or more objectives, Discover will actually load up those objectives, or the last 2 on the X and Y axes, so we can start to visualize these trade-offs right away. Now when we hit isolate optimal, you see that we don't just get one design, right? We get a bunch of designs that are on this Pareto front. You can compare the designs that are optimal and the ones that are not. And you remember this from the last couple of weeks, right? This x-axis right now is mapped to surface area, and the y-axis is mapped to volume. So we want to minimize surface area and maximize volume. Here is that utopia point, right? This is the kind of impossible design, and any design that starts to get close to this is optimal, right? And if we look at these designs, we can remember that non-dominance criteria, right? That this design is part of the optimal set because there's no other design that's better than it in both of the objectives, right? This design is better in terms of having a smaller surface area, but this one is better in terms of having a bigger volume. You can see that kind of step along that front, right? If we had another design here, this one would no longer be optimal. Okay, if we were going to run this for longer, we'd see a much more defined Pareto front. But I'll let you run that on your own. Any questions? Cool. So that's the basic distinction between a single objective problem and a multi-objective problem. Okay, the next thing I'm going to do is show you another example. And we're going to load up an example called the grid. So the Grasshopper samples grid. Okay, so this is already set up for Discover. I have all my nodes, and I have this manual inputs gene pool as well. So let me just load up an iteration here. We have our Discover viewport. I'm just going to change the view quickly so you can see this. So this is a bit of a weird example. It's pretty abstract, but it gets at some of the kind of spatial problems we'd like to solve and see if Discover can actually do this for us. So in this example, we're creating 25 points, these dots, And we're assigning to each dot a value, a categorical value, 0, 1, or 2. Right? So those are the numbers that are assigned to each dot. And then we're looking at the distance of each dot from the midpoint here. Right? So this dot will be 1 distance away, this dot will be 2 distances away. And then I'm basically subtracting the value of the dot, so this value is 0, minus the distance, taking the absolute value, and then summing all those numbers up. I'm going to minimize that value. Again, it's pretty abstract. It's kind of geometrical toy problem because the solution to this problem we know, right? We want to put the smallest value dot here, values dots with value 1 dot away, and then values 2 dots away. That'll give us the minimization of that function. It'll basically have the values of the dot match the distance that are away and give us that kind of bullseye figure. If you want to look at this, it's a pretty simple definition. Here we're creating the points. There's the midpoint. We're calculating the distance. This is subtraction. So we're taking the values, subtracting them from the distances, absolute value, mass addition to sum them all together. And that's our single objective. What we want to see basically is, we know the answer, but the algorithm doesn't, right? The algorithm all knows is like how to compute that metric. And then also it knows that it can take each dot and change the value. So we have 25 input parameters with a categorical input of 0, 1, or 2. And we're going to see if we can actually just flip the values for those dots and arrive at that answer. Okay, so to make this work, we want to set up our input parameters. So I'm going to reload the browser here. For our objectives, it's going to be very simple, just a single objective to minimize it. So we're going to keep that the way it is. Here we're going to change our input type to categorical. For the length, we want 25 input parameters. And the number of options is 3, 0, 1, or 2. Remember, for categorical inputs, you just have to say how many of those things are. And it's always going to create a list starting from 0 and 1 minus that number, or that number minus 1, right? So if we say we have 3 of something, it's going to give you options of 0, 1, or 2. And then you have to figure out how to map that in Grasshopper onto something you want. Okay, so those are our inputs. I'll hit test here just to make sure we're generating the right inputs. So here they are coming in. It's the same exact nodes I used before. I'm going to connect those into my input in Grasshopper. Now I can hit test a couple times and see. Oops. I want to change that view. And then I'm going to see these points get updated. Okay, so now that's being controlled. And I have everything set up. So I'm going to run the optimization. I'm going to run it for a little bit longer, and then we're going to load in a previous data set that actually optimized to see if we can get to the right solution. So we're just going to run this very small example. Hit start. Now, as the optimization is running, this has already been preloaded with the right name. So I can hit load data, and it'll load up whatever data there is at the moment. I can keep hitting this load data as the optimization is going to get the most recent data. So here we can kind of see dynamically what's going on, right, as it creates different generations. So this is a bit more complex problem. It's not going to be solved in this short optimization. And the question of how many designs and generations is right, it really depends on the problem. Typically, when I start testing, like a 4x4 or 5x5 is a very basic thing. Like it's just to make sure the optimization is working, your parameters are getting input correctly, and your objectives are coming out correctly. When you start to actually want to optimize something, even at this complexity, you want to start to bring these up. Maybe something like 20x20 or 50x50. Typically for like a big problem, I'll do 100x100 as a minimum. You can just multiply those numbers together and you'll understand how many designs will need to be calculated by Grasshopper. So for the 100x100, that's 10,000 different designs, right? And how long that takes depends on how long your grasshopper model takes to compute. So here, optimizing your model becomes very important as well. It's almost like when you're rendering a video, right? One frame might take only a minute, but if you start to think, like for 10 seconds of video, you have 30 frames per second, 300, all of a sudden take 10 frames, takes 300 minutes, and you have to kind of figure out how long that is. It's the same thing for optimization. We're going to be doing this over and over for these designs. Okay, so I'm not going to run that optimization now, but I'm going to show you the results by loading in the data from a previously run optimization. And I have the optimization run in my data folder, and exactly how it would have been created if you ran the thing yourself. Oh, never mind. I think I deleted it. Oh yeah, I didn't actually save out the grid. Bear with me for a second. Okay, so I have my grid. Let me just restore all these. Okay, this should be the one. So this is coming from the zip files that are uploaded to Dropbox. So you should be able to download it, unzip it. And if you want to use it, just put it back into your data folder. So as a reminder, the way these things are laid out is every time you run an optimization, it's going to create this folder. This folder's name is the same as the job ID down here. So it'll be the name of your Grasshopper file, followed by the date, followed by the time that it started. It should always be a unique number. And you have one file here. This is the actual data file. So you can open this in the text editor. And it's a human readable file. It's just a tab separated database. It's like a CSV, but with tabs. And you'll see the ID, the generation, the parents, whether it's feasible or not, and you'll see all the inputs. So here are my 25 inputs and the single objective. So the Explorer in Discover is actually just parsing this file, right, but using JavaScript. So it's made to be very transparent. There's no like databases or anything happening. So if you want to build your own tool for visualizing these things, you can just go directly from this data set. And it has everything available to you. And then there's also a folder with images, and this will be every design screenshot, and the name is the design ID. And again, Discover is just pulling those images dynamically from that folder. Okay, so let's load this up. If I want to load a previously run optimization, I just have to copy the name from the folder. I'm just going to paste that in here and go to load data. You see this beautiful plot. This is what we expect to see with a single objective optimization. Remember, x-axis is organized by generation, and on the y-axis, we're looking at the objective value. Right? And what we can see is over time in each generation, every few generations, there's a better and better design. So we can scrub over this and see, like in the first generation, we just generated like 20 designs randomly, so we're not expecting it to be very good. It's more or less random, but each generation gets a little bit better, a little bit closer to our bullseye sort of result. You see it's starting to organize the red one, around, and then eventually it gets the best solution. This is actually not the right one. Let me see if I can get it. Okay, this is the one. I had a little bug in the code, just making that solid blue one. So this is the final run. So you can see after about 23 or so generations, looking at 20 designs each generation, it's able to find that design. Now I know that's the best design, right? So I'm just testing this thing. You're not gonna know this in your case. If you already know the solution, you shouldn't be doing this at all. So when we do this for real problems, you know, we have to decide how much assurance we have, like how confident we are that this is the best design. In any case, I'll show you the best one that's done so far. But whether or not it's the ultimate best one, you never really know, right? So you want to try this different times, different settings for number of generations and things like that. If we go to isolate optimal, you see there's just one best design here. Any questions? So this is a categorical example. And remember, with these kind of things, we want to specify whether the input is continuous or categorical. Now, in this case, if you remember when we discussed the difference between the two, we said that continuous parameters should be used anytime where there's a continuous relationship between the input and the phenotype, like how it's expressed in the model. In this case, you can argue that these parameters should actually be continuous, right? Because you have 0, 1, 2. We're using them to calculate the difference in the distance. So there's a continuous relationship. And in fact, if I had them as continuous parameters and then rounded in Grasshopper, we might have achieved the results faster because it would know that, you know, if two designs, there's a kind of relationship between the value in that dot and the performance of the design, right? But I really want to test this categorically, say that even if it doesn't know that what it's changing are values or has anything to do with distance, just by flipping those values and picking randomly from different parents, if you can actually achieve the best results. So it's kind of a test of that type of parameter. Okay, to finish up, let's look at one more example. We're going to look at the third type of parameter option we have, which is a sequence parameter. So remember, the sequence parameter is very special. It's not just about the type of number we're using, right? With continuous and categorical, it's just the difference between a decimal number and an integer. And we can always select the length or the number of those parameters we want. Now with a sequence parameter, it's a little bit different. We always have 2 or more numbers in the sequence, and this relates to the order of something. So if we have 10 options in the sequence, it'll give us an ordered list of 0 to 9, right? And this ordered list we can use as a parameter for any model that is trying to figure out what the best sequence of something is or what the best order is. And remember, one of the most well-known examples is the traveling salesman problem. So I have a demo of that traveling salesman problem included with Discover, so let's take a look at it. Go to samples. This one has a Rhino component, so I'm just going to open that file in Rhino. Now, the Rhino file is pretty simple. It just has the outline of the states and a bunch of points. One for the start in New York, and then we have this set of cities that we're going to visit, and then there's a bunch more cities if you want to try more difficult travel and salesman problem. But to start with, we just have 10 other cities that we're going to go to after New York, and then we're going to come back to New York. We're going to measure the length of that route. Okay, so in Grasshopper, I'm going to load up traveling salesman as well. Okay, so let's take a look at this model very quickly. It's already set up for Discover. Here's the outputs, and we're looking for a sequence of 20, not 25. So these are the outputs coming from the grid still, right? So in this case, I know that I have 10 cities, so I'm looking for an ordered list of 10 integers. So I'm going to go here into Discover, reload, and then for my input, I'm going to do sequence, number of options 10. So right now we have 10 cities, so we keep that default. You set this to whatever you need for your model. I'll hit test. Okay, so now we're getting the proper inputs from Discover. If we hover over here, we see we have 10 numbers, and they're all unique integers from 0 to 9. And so this is what we expect. And now we're using that list to actually pick cities from the list of cities from our Rhino model. Right? So this is how we're using that parameter to create that route. We have these city points. There's 10 of them. And we're using the list item selector to select the city from that list that's in that position. And so this is how we're using that sorted list of integers to actually pick cities in an order. And by changing the order of that list of integers, we can change the order of the cities. Right? And then we merge that with our starting point, which is New York, and we just draw the polyline between them. Here I'm visualizing it in red. And then I'm just measuring the length of that polyline. And that length becomes my single objective that I'm passing into Discover. Okay. So I can hit test a couple times and see that the route is being generated. Now, before I run the optimization, I need to set my outputs. So I just have one objective. I want to minimize it. I can rename it if I want. And then, once again, do a kind of pretty simple optimization. This is 10 by 10. It'll be 100. I probably don't want to wait that long right now. But we can play it out for a little bit, and then I can stop it and show you an optimization I ran earlier. Okay, so let's hit start. It's going to start to generate our routes. I can load the data, and now I can sort of dynamically see this in action. So we're still on our first generation, so we're not going to get anything on the x-axis yet. We can see already the first set of random designs being generated. Load the data again. So there's our second generation. And we can kind of watch this. One tip is we can hit this button to reload the data from wherever it is currently. And if we hit isolate optimal, it's actually going to keep that setting as we reload data. If you want to just keep track of like, okay, have I improved? You can keep isolate optimal set and then just hit reload, and it'll tell you if like something in the latest generation has been found. In this case, we're not doing so great, right? We have the optimal one was found in the first generation, and we haven't been able to do better yet in 4 generations. And this is typical, right? You might get these kind of situations, and there's a lot of sort of intuition that starts to happen at this point about if something's not working the way you thought, why isn't it, and what can I do better? And we'll kind of review these cases as we go over the next couple weeks. So for example, here, I might say, well, I never got better. It looks like I actually did get better just at the very end in the last generation. Let's toggle up. It seems like my last generation did like amazing. You know, and because this is like kind of stochastic randomized algorithm, you're never going to be sure this is going to happen this time or ever again, right? The process that it takes is more or less random. The only assurance we have is through those behaviors of the algorithm, there's a tendency for it to get better and better over time, right? But in this case, like if we didn't have this amazing last generation, in fact, we still don't have the best design, right? I can say, well, what can I do? One is I can run the optimization for longer, right? So I can give it more of a chance, or I can give it more time to evolve, right? And so it can take more iterations to do that. But the thing you always have to remember is it can only work with the designs in the generation before. So the size of each generation, the number of designs per generation, dictates how much diversity the system can keep in memory, right? And so both of these are really important. The number of generations tells you how long the evolution can take place for. So you definitely want to do that, you know, as long as possible. But also you want to maintain enough diversity in each generation to make sure you don't get either convergence on like a local best solution, or even worse, a divergence. You know, if you don't have enough designs in the generation, you can actually lose good data from one generation to another, or there just won't be enough diversity to actually find anything useful. All right, so it looks like we had one kind of big step. This is kind of weird, actually. We just had one point where we found a bunch of better designs, and then it wasn't able to improve. After that, again, this is pretty small. 100 designs is probably not enough to solve this problem, right? But it's not bad, right? It's probably even better than our heuristic. So if we do run this for longer, I ran this for, I think, 30 by 30, and it was able to find the best design that we know. And I can load that up here. I have my TSP example that generated last night. So I'm just going to copy and paste the name of that folder. As long as it's in this data folder, I can just copy and paste it here. and load the data. And there it is. Right. So I ran this. I think there's 30 designs, 20 or 30 designs in each generation. And you can see here that actually by the 9th generation, it's able to find that best route. And then the optimization kept running, and of course, it's never going to find anything better than the best. So we're just using this to see basically how quickly it was able to happen. And there's no guarantee it's going to happen in the 9th generation. Like when I ran this before, it took a little while longer. Like the best design was at like design 800 or something like that. But it's a kind of test to make sure that at least we can solve this type of problem using Discover with these sequence input parameters. Okay, any questions about that? Sequence parameters, traveling salesman problem. Anybody who's doing a project around routing or locating things. Another really useful application for these kind of sequence parameters is programming, program placement. So if you have, instead of a travel route with 10 cities, imagine you have a floor plan with 10 different spaces, and then you have 10 programs that you want to assign to those spaces. So this is a kind of assignment problem. It's a classic space planning problem. And you can use these kind of parameters to actually figure out the order in which to place those programs. So if you keep your list of spaces fixed, and then you have your list of programs, you can use that sequence parameter to shuffle those programs into those spaces and then test for the best one. Yeah. Yeah, it's a great question. So because all the operators, there's a lot of randomness built into the operators, every time you run it, you're going to get a different result. Now, the mapping between inputs and outputs in your model should always be the same. So if you put in the same inputs, you should always get the same outputs. So there should not be any randomness in the model itself. If you have any randomness in the model, there's no way for the optimization to happen, because you can imagine the system will never be able to learn, right? If every time it inputs the same parameters, it gets different results. There's no optimization hope. So for your models in Grasshopper, there can't be any randomness. But in the way the optimization works, there's a lot of randomness, right? That's why it's a stochastic algorithm. So when it picks parents, it picks it randomly and then chooses the best ones, right? So every time you run, it's going to be different. It is possible to set a random seed in the optimization to ensure that you get the same results. So that could be a feature actually, that if you do want to replicate exactly the same experiment, you can actually set the same random seed. So even though the decisions are random, it makes the same random decisions, right? In this case, I don't have that implemented because usually you want it to be different each time, right? Unless you're like replicating someone else's experiment. Every time you run this, you want a different case, because again, like I can run this and never finds the answer. It doesn't mean that it can't. It just means that maybe that run wasn't successful. And if I run it again, there's more of a chance it does the right thing. Yeah, yeah, exactly. So the way Discover is now, you can't set that seed or anything like that. It's always going to be different each time. It should be similar, right? The trend should be the same. Like it won't be all of a sudden, like the behavior of the genetic algorithm won't change. Like it won't start picking bad parents all of a sudden. It'll still do the same process. It'll still tend to get better and better, but you can never predict. You see in the last run, it's like one generation, all of a sudden they made like 5 better designs and then no more. And you don't know. It's just the kind of luck of the draw, literally.